Now let us discuss about one of the innovative concept, and that is called as geopolymer concrete. Geopolymer concrete. Geopolymer concrete. Right. So this geopolymer concrete is an innovative, eco-friendly construction material. So concrete, the word concrete is there. Based on that, we can say that, right? It is used as a replacement, right? It is used as a replacement for conventional cement concrete, right? Conventional cement concrete. So why? Because it is responsible for the emission of carbon dioxide. Carbon dioxide is a greenhouse gas. So that's why we have to, this gains lot of importance. That is geopolymer concrete. It is an innovative, eco-friendly construction material. So if you come and see the composition, right? Composition of this geopolymer concrete, right? If you come and see the composition of this geopolymer concrete, right? So it can be listed like this, right? So it consisting of a source of, one is source of aluminosilicates, consists of source of aluminosilicates, right? Source of aluminosilicates such as, right, such as fly ash, right, such as fly ash, GGBS, ground granulated blast slag. GGBS means ground granulated blast slag, right? And then metacolloid, right? And then last is silica, right? Silica. Second one, if you come to see the composition, it consisting of alkaline material or alkaline solution, alkaline material such as NaOH or KOH, NaOH or KOH. So its composition, its concentration will be from 8 to 14 molar. You can take up to 8 to 14 molar. So coming to third one, the next one is alkaline activators. Next one in this composition is alkaline activators. These alkaline activators are usually silicates of sodium and potassium, right? Silicates of sodium and potassium, they are called as alkaline activators, right? So alkaline activators. And at last, the last composition is water. So water, it is used only for dissolving or making alkaline solution, and it is released during geopolymerization, right? So these are the composition of geopolymer concrete, right? So if you come to see the ingredients which are taking during the synthesis of geopolymer concrete, the same ingredients, it is there. In short, we can say, if you can write that ingredients in the other name, right? So it can be like sources of aluminosilicates in the first ingredient, same sources of aluminosilicates, right? Aluminosilicates, and then the other ingredients will be sand. We have to use sand here. And third one is water. And the fourth one is hydroxides such as sodium and potassium. That is NaOH or KOH. And at last is silicates of sodium and potassium. Silicates of sodium and potassium. So these are all the ingredients, the same composition only we have taken here in order to synthesize this geopolymer concrete. These are the ingredients that must be used, right? So now let us see the synthesis, how one can synthesize this geopolymer concrete. So let me explain the tell the process first. So here in the synthesis of geopolymer concrete, so we have to take one alkaline solution, and it should be mixed with a proper proportion with the silicates of sodium, such as Na2SiO3, right? That is silicates, right? So NaOH in the concentration of 8 to 14 molar, you have to take it as an alkaline solution, and it should be mixed with silicates of sodium, so in a proper required proportion, as a result of which it undergo exothermic reaction with the liberation of heat energy, and thereby it is going to form highly alkaline solution. So from this highly alkaline solution, you have to allow this highly alkaline solution to cool to the room temperature, right? It requires usually around 24 hours to get cool to the room temperature. Then you have to mix that highly alkaline solution with other ingredients such as silicates, aluminosilicates, sources of aluminosilicates, and sand, right? So that if you maintain a temperature of 60 degrees Celsius, it undergoes geopolymerization, that is polycondensation reaction with the liberation of water molecules, and if you are curing and mixing that is properly, so you are going to get geopolymer concrete. So this is the process it is involved in the synthesis of geopolymer concrete. So let me write that. So on one side you have to take alkaline solution, right, of concentration 8 to 14 molar. So alkaline solution means here we are going to take NaOH for explanation, right? You can take, and then plus what else you have to take? You need to take 1 silicates of sodium, right? So silicates of sodium or potassium, right? Here I am going to take this sodium silicate, right? Sodium silicate. So if these two are mixed properly in a required concentration, so an exothermic reaction will be taking place with the liberation of heat energy. Exothermic reaction will be taking place, and that will give rise to highly alkaline solution. The resulting product is highly alkaline solution. So this highly alkaline solution should be allowed to cool to the room temperature. It is taking around 24 hours to get cooled. After that you have to mix this with sources of aluminosilicates like this, right? So they are called as sources or are precursors. Usually they are called as sources or precursors. So that's why sources of aluminosilicates, right? And then you have to mix with aggregates, right? Aggregates such as sand, right? You have to mix, and then so if you maintain a temperature of 60 degrees Celsius, it undergoes polycondensation reaction. So polycondensation reaction, so if properly mixing and curing, if you have to do this, so you are going to get geopolymer concrete. It is a highly innovative, eco-friendly construction material. This is the flow chart of the synthesis of geopolymer concrete. Understood? So you have to take one alkaline solution in this molar concentration and silicates of sodium or potassium, and if you properly mix these two, you are going to get through an exothermic reaction, you are going to get a highly alkaline solution. If you treat this with or mix this with sources of aluminosilicates and aggregates of such as sand, so it undergoes polycondensation reaction at 60 degrees Celsius, we are going to get geopolymer concrete, right? So it is of very much useful. It exhibits excellent properties compared to conventional cement concrete, right? So for that purpose, if you can see the properties we can list out like this. So we told that it is an innovative, eco-friendly construction material. So that you can write as one property, right? So the major properties are, it is non-toxic. So that's why it is eco-friendly, it is bleed free, right? So eco-friendly, why? It does not emit, does not responsible for the emission of carbon dioxide, right? So it it sets at room temperature. This is very, very important, right? So it is non-toxic, right? It sets at room temperature, right? Remember. So third important property is it is having high compressive strength. What? It is having high compressive strength. High compressive strength, remember. So compressive strength, and coming to this, it is highly resistant to the action of any inorganic solvents, right? Or any the action of heat or temperature. So it is resistant to the action of heat or organic solvents, right? Remember. So coming to the fifth important property, so it is impermeable. This is very, very important. It is impermeable. So as it is impermeable, remember, as it is impermeable, it provides a very good, it acts as a very good protection. It provides a very good protection for the reinforcement of steel from corrosion compared to conventional cement concrete, right? So it is highly impermeable. Coming to the last one, right? Shrinkage, right? So shrinkage or drying of GPC is much less, right? Drying or shrinkage, okay, drying or shrinkage of GPC. GPC means geopolymer concrete. You can call in short like this, so that easily you can remember, right? So all these properties made this geopolymer concrete can be used for so many and variety of applications, right? So if you can see the applications, we can list out the applications like this, right? As it is a cement, as it is a concrete, it can be used for the construction of variety of flyovers, highway structures, bridges, right? Similarly water tanks, right? Pavements, and then walls, right? Etc. You can synthesize. So that and all you can list out, right? Used in making flyovers, right? Highway constructions, right? Highway constructions, used in making bridges, right? Bridges used in making pavements, right? So used in making water tanks, right? So etc. You can list out like this. Okay, so walls, right? So coming to the second application of this geopolymer concrete, so it is mainly used in the manufacture of railway sleepers and sewer pipes. In the manufacture of railway sleepers and sewer pipes, right? Sewer pipes. And so next very important application is, as it is a structural material, it can be used in manufacturing in making of column beams, right? Or in the tunnel construction, right? So tunnel construction also you can use, right? Column beam and tunnel construction, right? And tunnel construction. So like that, it can be used in making flyovers, highway constructions, bridges, everything. So because of the non-toxic in nature, as it is stable and environmentally friendly, it is better to use this. So in this way one can understand the composition, ingredients, synthesis, properties and application of geopolymer concrete. Next polymer is biodegradable polymers. Biodegradable polymers. Right. So what are these biodegradable polymers? In the name itself it is there, right? Meaning is there, right? See, biodegradable polymers can be defined as, right? So these are the materials whose physical and chemical characteristics undergo deterioration and completely degrade when exposed to microorganisms, aerobic and anaerobic processes, right? So such polymers are called as biodegradable polymers, right? So these biodegradable polymers are also called as biopolymers since because they are derived from natural resources, right? They are also called as biopolymers because of they are obtained from natural resources such as sugar cane, corn or starch, etc., right? So that is a thing. So in biodegradable polymers there are two types. One is natural biodegradable polymers, the other one is synthetic biodegradable polymers. In a natural biodegradable polymers, right, they are synthesized or they are present in the nature. They are produced by, synthesized by almost all the living organisms, right? So that type of polymers are called as natural biodegradable polymers. The examples are polysaccharides such as starch and PHA, that is polyhydroxyalkanoids, are the very best example for natural biodegradable polymers. Coming to synthetic biodegradable polymers, they are synthesized by mankind, right? So usually this type of synthetic biodegradable polymers are the consisting of, see, aliphatic thermoplastic polymers that consisting of easily hydrolyzable linkage, and the best example for synthetic biodegradable polymer is polylactic acid, right? That is polylactic acid. So polylactic acid is a biodegradable thermoplastic aliphatic polyester, right? So this polylactic acid is a biodegradable, right? If we can list out this property, it is a biodegradable, right? It is a biodegradable, right? And thermoplastic, biodegradable thermoplastic aliphatic polyester, right? So it is one of the very best example for synthetic biodegradable polymers, right? So before going to study the synthesis properties and applications of polylactic acid, now let us understand what are the requirements for these biodegradable polymers. So coming to the requirements, so if you can see the requirements, right, what are the requisites for a polymer in order to become biodegradable polymers? So the requisites are, they should be stable. The first requisite is they should be stable, right? They should be bioadsorbable, they should be biocompatible, right? So they should be non-toxic and they should exhibit good mechanical integrity until degraded. They should be exhibit good capable of controlled rates of degradation. So all these properties are or requirements are essential for a polymer in order to become biodegradable polymers, right? So they should be stable, biocompatible and bifunctional, right? So second, this one is bifunctional. This is also important. So like third one is bioadsorbable, biocompatible, capable of exhibiting good mechanical strength until degraded, non-toxic and then capable of controlled rates of degradation. Remember, these are the requirements. So with these requirements, now let us move towards the synthesis of polylactic acid. Let us move towards the synthesis of polylactic acid. So if you see the synthesis of polylactic acid, in short it is called as PLA, remember, right? So first of all, let us understand how lactic acid is prepared, then we can go for the synthesis of polylactic acid, right? So polylactic acid is a biodegradable thermoplastic aliphatic polyester. As I already told, it is derived from various natural resources such as corn, starch, sugar cane, etc. Right? Sugar cane, etc. Right? So this lactic acid is produced by bacterial fermentation of the sugar cane. So in that way we are going to get the lactic acid, right? Lactic acid structure is like this: CH, CH3, OH, COOH. This is called as lactic acid. So if you can see the structure, it is bifunctional. It consisting of two active functional groups. That's why it can act as a very good monomer for the polymerization, right? So this lactic acid is prepared by bacterial fermentation of sugar cane or by conversion of starch to corn. It will be prepared. So once lactic acid is prepared, it is oligomerized and catalytically converted into lactide monomer, right? It is catalytically converted into lactide monomer. So then from the lactide monomer, high molecular weight polylactic acid is prepared by ring opening polymerization in presence of stannous octanoate as a catalyst, right? So that we can see now. So first I will write a simple way of synthesis of this polylactic acid, and then we can take up the other way, that is by ring opening polymerization. That and all we can take up, right? So if we can write here, so this undergo condensation polymerization, right? Condensation polymerization with the elimination of simple low molecular weight compounds such as water, right? So if we can take n moles, so that the product obtained is OCH, CH3 and then C double bond O, right? So this itself is called as polylactic acid in simple terms, right? So but the same polylactic acid, as I explained now, so you can it has to pass through the lactide monomer, right? And ring opening polymerization lactide monomer will give us the polylactic acid. So that's why I will take this in this form: CH, CH3, OH, COOH, right? So this lactic acid, the same lactic acid I have written in a different way. So lactic acid, it is oligomerized and catalytically converted into lactide monomer. So if you can write the structure of lactide monomer, so it will become like this, right? So I will write it here: CH, CH3 and then C double bond O, right? And O, and here also O, and then CH, CH3, C double bond O and O. So this type of lactide ring is going to form, lactide monomer is going to form, right, after it has subjected to oligomerization and catalytically converted to lactide monomer. So this is called as lactide monomer. Actually we have to understand through this mechanism so that you will not forget. So this lactide monomer now undergo ring opening polymerization here, right, in presence of stannous octanoate as a catalyst, right? Stannous octanoate as a catalyst. So we are going to get polylactic acid. So that I will start from this. It is O, CH, CH3, then C double bond O n times, right, and then O, CH, CH3, C double bond O, right? Likewise the chain continues, and this structure itself is called as polylactic acid, right? Or else I will write the full form, that is polylactic acid, right? So remember Actually, one of the drawback of our polymers are they are not biodegradable, right? So they are producing lot of pollutants in the environment every day. So that's why we have to move towards these biodegradable polymers. Otherwise, we cannot able to prevent the pollution. So in such a direction, polylactic acid plays very important role, right? So this is all about the synthesis of polylactic acid through this lactate monomer, and by this is called as ring opening polymerization. Ring opening polymerization, right? It is occurring through ring opening polymerization. This is oligomerization, right, and followed by condensation polymerization with the elimination of simple molecules. We are going to get this, right? I hope you understood. See, coming to the properties of polylactic acid, so let us see one by one. Properties of biodegradable polymer such as polylactic acid, right? So polylactic acid is a biodegradable thermoplastic aliphatic polyester, as I already said. So if you look at the properties one by one, so it is an highly versatile thermoplastic polymer, right? It is highly versatile thermoplastic polymer. So I already told what is thermoplastic materials, right? Thermoplastic polymers are the one which softens on heating and stiffens on cooling. So coming to the second property, these polylactic acid are made from 100% renewable resources. Made from 100% renewable resources, right? So that is the thing. And coming to the third properties, right? So it is insoluble in water, moisture, and it is grease resistant, right? So it is insoluble in water, moisture, and grease resistance, right? And the fourth property of this polylactic acid is it is biodegradable and compostable, right? Biodegradable and compostable, that I already told. So biodegradable and compostable, right? And coming to the clarity and glassiness, they are very similar to the other type of polymers. And then the sixth one is it requires around 15 to 20% less fossil fuels, right, in order to produce. So that's why they are environmentally friendly. And at last, right, these polylactic acid, they are highly crystalline and they are having high melting points, right? So these are the properties of polylactic acids. Coming to the applications of polylactic acid, right? So these polylactic acids are used in biomedical implants, right? So in the form of in the form of plates, screws, rods, right? So etc. they are used in biomedical implants, right? In the field of biomedical, as used as biomedical implants. And in the field of biomedical applications, these polylactic acid found applications in sutures, stents, dialysis media, and in drug delivery devices, right? Drug delivery devices. And coming to the third application of this polylactic acid, they are used in disposable garments and diapers, right? Disposable garments and diapers. And the fourth one is they are used in disposable food packaging and tablewares and compost bags, right? These are all the some of the very important applications of this polylactic acid.